Today we're going to talk about rational exponents. And if you remember what a rational number is, a rational number is simply a fraction. So we're going to look at rational exponents, which is going to translate to exponents that are fractions. Nothing to be scared about. Some people get worried about that, but they're really not too bad. Okay. First of all, you guys are familiar with some radicals, like the square root of 4. Okay, when we say that number, we say the word square root, and technically there's a little number right here that I call in the index. Okay, that's a little 2. And normally we don't see a 2 there. Kind of like when you see an x. X, it doesn't have an exponent on it, but it's really x to the first. And really also has a coefficient out there in front also of a 1. And but again, we usually don't write it that way. We're just usually going to see it as a plain old x. Well, same thing with radicals. Okay, if there's no number in front in the little index here, it's assumed that it's a 2. So when I look at this one, I have a little 2 there. It's the square root of 9. And then 9 also has a little exponent on it, 9 to the first power. And here's how we convert from radical form to exponential form. Okay, it's going to be 9 is my base number, and it's going to be raised to the 1/2 power. And if you notice carefully there, where did the 2 go? The index number became the denominator of the fraction. And if there's an exponent in here, it became the numerator of the fraction. Okay, so it's a pretty simple little conversion. When I look at the 16 there, the second one, again, I don't see a number, but it's the square root of 16 to the first power. It's going to be 16 again to the 1/2 power. And lastly, same thing over here on the x. There's a little 2 there, a 1 on the exponent, and we can rewrite that as x to the 1/2 power. Okay, so let's go to my second row of numbers here. Okay, notice these are all cube roots. We can do the same exact thing. There's a little 3 for cube root of 8 to the first power. Well, it's 8 to the 1/3. Okay, the cube root of x to the first is x to the 1/3 power. Okay, now this last one here's a little tricky. You have to be a little careful with that. If you look closely, there's more than just one thing under the radical here. Both the 5 and the x are underneath the radical. And the way we kind of note that then is we put the 5 and the x in parentheses. And that is being raised to the 1/3 power. Okay, so kind of technically it looks something like this. 5 and x are both to the first power. The denominator comes from the root. The numerator comes from the exponent. Okay, so converting into exponential form isn't too terribly bad. Now, way down here at the bottom here, I kind of have a general rule. Whoops. For converting to exponential form. Okay, if I have the nth root of some number a, it becomes a to the 1/n power. Okay, and there we have it. So the first thing we're going to encounter down the road here is we're going to have to convert into exponential form. Okay, these next ones here, I'm going to go backwards. Okay, what if I have an exponential form and I want to convert to radical form? Well, we're going to do the same thing, just in reverse order. I'm going to have a radical here. I need a root. If you remember, the root came from the denominator, so it's the square root of 25. And if we want to put the first power, we sure can. Don't necessarily have to. Okay, here I have a 1/3 power. That tells me it's the third root of 216 to the first power. And the last one over here is a 5th root of 32, or 5th root of 32 to the first power. So again, going the other direction isn't so bad either. The second row of numbers here, if we look carefully, it's kind of like the last one I did in the last screen. There's more than just one number or one letter being raised to a power. Okay, so in my radical here, I can see it's going to be a square root. And what's being raised to the 1/2 power? The 7 and the x. So they both have to go underneath the radical. Same thing is true with this one. I have a cube root. You notice there the denominator's a 3. Both the 4 and the x are being raised to the 1/3 power, so they both have to go underneath the radical. When I get to this last one here, now look carefully at that one. It's a 1/4 power, but the question that we have to ask ourselves is what's being raised to the 1/4 power? Is it the 9, the x, or both of them? Well, there's a difference between this one and this one. Notice that one has parentheses, meaning everything is raised to the 1/3 power, but this one does not have parentheses. And when the 1/4 is only going on the x. So when I write my radical here, it's only the x that's going underneath there with the 4th root of that. Well, that begs the question, what about Mr. 9 out there? Well, 9 is just timesing x, so 9 is just a multiplier out in front. and it stays out in front of that radical and not underneath it. Okay, so we have to be careful whether or not there are parentheses, because it can make a big difference. Okay. All right, very nice. So we've converted from radical form to exponential form to radical form. Okay. I have a special one down here. A couple special ones also. How about negative exponents? Negative fractional exponents. Well, previously we've talked about how to deal with negative exponents, and the way we make a negative exponent positive, if it was negative on the top, we moved it to the bottom. And if it was negative on the bottom, we move it to the top. Well, we're going to do the same thing. This is starting out as 36 to the negative 1/2 over 1. And like I said, we don't like a negative exponent, so it's going to move down to the bottom. And it's going to become 1 over 36 to the positive 1/2 power. Okay, if you look carefully at that, notice the 36 didn't change signs. It was just the 1/2, just the exponent that became positive. The 36 still stayed positive 36. And same thing with this guy. This starts out over 1. A negative exponent, it's got to go down to the bottom. And it becomes 1 over 8 to the positive 1/3 power. Okay? Now, for our class, for our purposes right now, we're going to leave it with a fractional exponent in the bottom. Later on in the course, we'll talk about how to deal with that. Okay, but yeah, negative exponents, they just go down to the bottom. Okay? On our next screen here, okay, we're going to talk about how to simplify a radical that maybe isn't, or that's something besides a square root. In the past here, you guys have evaluated square roots of numbers. Square root of 25 is 5. The square root of 49 is 7. Okay, and if you are good with your math facts, you maybe just knew those. Good with your times tables. If not, you maybe used your calculator. And in dealing with things like square root of 25, you all know where the square root button is on here, and you would type in the square root, hit 25, and enter, and it would tell you 5. But when you look at something like this, like a cube root, I have a couple cube roots, a 5th root, a 3rd root, and a 4th root. How do you do those? Hey, now, is there a place where a cube root button is found? Not a button, but a place we can find a cube root on the calculator? Yes. Okay, if we dig in a couple screens, we can get to it. How about a 5th root? Yeah, there's a place where we can do a 5th root as well. But it's a couple screens to get to, and personally, I think it's a little bit easier to do it this other way. We have 2 options, actually. Okay, first of all, we can do what we've been doing in the last couple minutes here. Could I change the cube root of 27 to a fractional exponent? Well, I sure can. That would be 27 to the 1/3 power. Okay. Well, hey, can we do exponents with the calculator? Sure. We can pick it up. We can type in 27 raised to the 1/3 power and hit enter, and it's going to tell you 3. Okay, I'm just going to refresh your memory. How do you type that in the calculator? Well, it's 27. Then you hit that little caret key, raised to. And how do you do 1/3? As you know, all fractions, no matter when and where you use them, have to be in parentheses. So it's 27 parenthesis 1 divided by 3. Close the parenthesis and hit enter, and it's going to tell you 3. Okay? We could do the same exact thing with a 5th root. The 5th root of 32. I could rewrite that as 32 to the 1/5 power. And I could type it in the same way that I did this one. And if I did that, it would tell you 2. Okay? Just like these guys over here. Okay. Now, that's not too bad changing it to a fractional exponent. But I want to mention another thing. In the resources that I listed at the top of the Google Classroom, resources you might need, there's this yellow sheet that looks something, well, I think on the computer it might look white, but it's this little half a sheet of paper that has perfect cubes and squares and fourths and things on it. And we'll hold one up close in front of the camera here so you can get a good look at it. If you look across the top, you can see there it says squared, cubed, 4th, 5th, 6th, and 7th power. And down the left-hand side are the numbers. Okay? So for example, what if I wanted to find out what 4 cubed is? If you go down the left-hand side to 4, and then go to the right over to where the cube column is, you'll see 4 cubed is 64. Well, we can use the sheet to go in reverse as well. Okay? If I was talking about the one back on the screen here, the cube root of 27, if you look carefully on your sheet, since I'm looking for a cube root, if I go over to the cube column and then go down to the cubes, down the list of cubes, and do I find 27? Yeah, it's the 3rd one down. And if you go way over to the left then, again, what number cubed is 27? You'll see a 3. Okay? If I did one more here, let's see if I can find the 5th root of 32. Okay? If you go way over across the top to the 5ths column, and go down the list, can you find the number 32? Well, there it is. It's the second one down. So what number to the 5th power is 32? If you go way over to the left, it's a 2. Okay? So that's how we can use this. I call it the yellow sheet. If you were to print it out on your computers, printers, whatever, it's going to be yellow. Okay, so I'm going to reference that a little bit. Okay, down at the bottom one here, number 2a, the cube root of 64. Again, rather than using my calculator and change it into a fractional exponent, what if I use my yellow sheet? If you go to the cube column, go down to 64, and over to the left, you would see that that is 4. The cube root of 64 is 4. Okay. Now the last one here, if we put this up on the screen, it's the 4th root of 10,000. If I go down the 4ths column, it only goes down to 4,096. You notice only half of this thing is filled in. Well, the reason only half of it is filled in is because the vast majority of the time, you're only going to use the numbers there kind of on the top left diagonal. Okay? But it might not be a bad idea if you have some free time to fill in the rest of it. And if you were to go down a couple more, 9 to the 4th power, and then one more 10 to the 4th power, you would see it's 10,000. Okay? And if I went over to the left, the 4th root of 10,000 would be 10. Okay? Or when in doubt, you could do 10,000 to the 1/4 power, and it would also tell you 10. Okay, we'll see here in a minute. Sometimes, personally, I think it's going to be a little bit faster to use this sheet to evaluate some roots and radicals. Okay, but you can always certainly use your calculator. Okay. All right, let's move on. Let's kind of tie all some of this stuff together here. It says rewrite each in radical form. And then ultimately what we're going to try to do here is we're going to try to evaluate each of the following. Okay, so now, yes, we can certainly type in 64 raised to parenthesis 2 divided by 3 and hit my calculator, and it would give me an answer. But I'm going to try to get you to practice using this thing a little bit. By using this yellow sheet, it's going to make you more familiar with some of the very common perfect squares, perfect cubes, and perfect fourths. Okay, so to help me with that, I'm going to change this into radical form. If you remember, the denominator is going to be the root. There's my base number, so it's the cube root of 64 squared. Okay, and if I use my sheet here, the cube root of 64 turns into 4, and 4 squared is 16 is what I would get my for an answer. And I get the same thing there if I use my calculator. Okay, and again, a lot of these you might know. This one, if I change it to radical form, it's going to be the square root of 36 cubed. Okay, well, the square root of 36 is 6. And if I did 6 cubed, I could certainly use this sheet, go down to 6, over to cubed, and it's going to tell me 216. Okay, and like I said, personally, when you get comfortable with this sheet, it's actually faster to use this than it is to type it in the calculator. Okay, but again, it's all personal preference. Okay, I got 2 other ones here. Maybe let's take a minute and see if you can try these 2 by yourself. So push pause on the video, and we'll give it a shot. And when you're done, unpause and we'll keep going. Okay, welcome back. Let's try this one. 27 to the 2/3 power. It's the cube root of 27 squared. Well, the cube root of 27 from your sheet is 3. And then 3 squared is 9. Yep. Okay, this one, if I did it, I'm talking about the 4th root of 256 raised to the 5th power. Now, this one's a little bit bigger number. If I look at the 4th root of 256 on my sheet, it's a 4. And I have 4 to the 5th power. And if I do 4 to the 5th power and I look at my sheet, it would tell me 1,024. And like I said, it's okay if you were to use your calculator to do these. Okay, but I'm really going to try to emphasize using this yellow sheet or this half a piece of paper. At least become familiar with a little bit, because you'll see here in a second where it will be a little bit more helpful. Okay. All right, so we've converted different forms. We've evaluated some exponents, some roots, fractional exponents. Okay. How about fractions? Can fractions be square roots, or can we do cube roots and square roots and 4th roots of fractions? Sure. Now again, it looks kind of scary, but let's keep it simple. And the ones we're going to see right now are going to be fairly nice to us. And here's how we're going to tackle these. If we have a fraction underneath a radical, and if you notice carefully, it's a 2 there, it's a square root. What we can do is we can just separate them. Okay? we can separate this into the square root of 9 over the square root of 25. We can literally make it two separate radicals, a numerator and denominator. And well, hey, I think they turn out to be pretty nice numbers. How about the square root of 9 is 3, the square root of 25 is 5, and I get an answer of 3/5. Yeah. So fractions aren't anything to be scared of. This one, I can separate into 2. The 4th root of 16 over the 4th root of 81. And again, to do the 4th root of 16, maybe use your sheet or your calculator, 16 to the 1/4 power, but it's going to tell you 2. Whoops. That should be the 4th root of 81. 4th root of 81 is 3, and I get 2/3. And yeah. Okay. How about this guy? This last one. Ooh, this one looks a little crazy. If you remember from the properties of exponents, this goes here, and it goes here. Now, it's not starting in radical form, but it's a fraction with a fractional exponent. Well, again, let's keep it separate. 84 to the 4/3 over 125 to the 4/3. Okay, separate it. Let's do each one separately. This means the cube root of 8 to the 4th power. Oops. It's a bit nicer here. The cube root of 8 is 2, and 2 to the 4th power is 16. Okay. Down here at the bottom, this means the cube root of 125 to the 4th power. The cube root of 125 is 5. And then up with 5 to the 4th power, if I look at my sheet, that's going to tell me 625. So it would be 16 over 125. Okay? All right, so yeah, so fractions aren't too terribly bad. Just separate them into two separate fractions. Two separate things, a numerator and a denominator. Okay? All right, here's our last thing that we're going to talk about. Okay? And we're going to solve equations that have with exponents. And there's a little exponential property of equality here. Okay? And if you can kind of look right here, it might be hard to see, but it says 5 to the x equals 5 to the 3rd. If I have the number 5, and they're both being raised to a power, and it tells me that they're equal to each other, okay, well, that means the exponents have to be equal to each other. Okay, and then I could just say, well, x has to equal 3. Okay, but the key concept here is the base numbers have to be the same. Okay, a little extension of this, just to kind of reiterate the point here. Okay, what if I had 4 to the 2x plus 3 equals 4 to the 3x plus 6? Okay, if you notice the base numbers are the same, they're both 4s. And the equation, those two things are equal to each other. Well, if they're equal to each other, that means the exponents have to be equal to each other. And we could write a little equation that says 2x plus 3 has to equal 3x plus 6. And then we can solve it. I'm going to do this really fast here, but I'm going to move my x's over to the same side. I'm going to subtract 2x. So I get 1x plus 6 equals 3. And then just to get x by itself, I'm going to subtract 6, and I'll get negative 3 equals x. X would equal negative 3. Okay? But again, the key concept here is that these base numbers have to be the same. And if the base numbers are the same, then we can just set the exponents equal to each other, and we're in business. Okay? But however, now, if you look carefully at this one, these next couple ones here, the base numbers are not the same. Okay, I have 5 to the x power equals 25 to the first power. The bases aren't the same. I can't say x equals 1. They're not the same. And here's the key concept for this last thing that we're going to talk about. We're going to have to change these numbers, change one of them and sometimes both of them, so that into a number that has the same base. Okay, and I oftentimes look at the big number. I start here at the big number. Can the big number be written as the smaller one to some power? And again, okay, that's where this gold sheet or yellow sheet can come into play. Okay, I'm trying to find, can 25, this is my question that's going on in my head, can 25 be written as 5 to some power? Okay, and if you look here on 5, down to 5 and you go across the right, well, yeah, 5 to the square, 5 squared, 5 to the second power is 25, is equal to 5 to the x. Okay, and if I look carefully here, the base numbers, hey, they're now the same. So the exponents are the same. X would equal 2. Okay, that's how this is going to kind of work. I have a couple other nicer ones here that I want to take a look at. Here's a second one. Okay, what if I had, let's see, 2 to the x power equals 16. 2 to what power is 16? Well, this has a base of 2, that's 16. Is there a way I can change 16 and have it be rewritten as 2 to some power? And if you look on the gold sheet there, 2 to the 4th power is 16. Yep. The bases are the same, so the exponents are the same, and x equals 4. But, and I've said this about 3 times already, but the whole key is changing the big number into the smaller number raised to some power. Okay? Oops. And here's another little example that's on there. What they did over here on the left is they changed 216 into 6 cubed. Okay? They both have bases of 6, so x equals 3. Okay? The one on the right here is a little bit trickier. You can kind of see how they changed. This is a base of 25, that's a base of 5. It's 5 to the 1st power. Okay? Well, they changed 25 into 5 squared. And then what they did is they multiplied the exponents using that multiplication property of exponents to get 5 raised to the 2x minus 2 equals 5 to the 1st. Well, now the bases are the same. So they wrote, the next step here is they wrote a little equation where the exponents were equal to each other. They added 2 and divided by 2, and x was equal to 3 halves. Okay, and we'll take a look at a couple like this here in just a minute. These are the last ones that we're going to try. Excuse me. Okay, so here's my last, I got about 2 or 3 of them here that I'd like to try. So look at this one. 16 to the 2x minus 1 equals 8. Ooh. Okay. Well, obviously this one has a base of 16, and this one has a base of 8. And as I said before, what I sometimes try to do is I ask myself, can the big number be written as the smaller number to a power? Now, a lot of people say, well, 8 to the 2nd is 16. Well, no. 8 to the 2nd power is 64. Okay, that's not going to work. I can't get 16 out of that. So again, this is where my yellow sheet comes into play. Okay, I try to find a column here, okay, that has 16 and 8 in it. I'm sorry, a row that has both 16 and 8 in it going across. Well, I see that 2 does. 16 can be rewritten as 2 to the 4th power. 8 can be written as 2 to the 3rd power. Okay, so I can rewrite them as I can rewrite both of them as base 2. Okay, this one just has a 1 up here, so technically it's like this. But 16 is still being raised to the 2x minus 1 power. Okay, and if I use my properties of exponents like we saw in the last slide, if I distribute here, that's 2 to the 8x minus 4 when I multiply to both, is equal to 2 to the 3rd power. Now when I look at these, they both have a base of 2. And when the bases are the same, I can set the exponents equal to each other. So I can say that 8x minus 4 is equal to 3. And if I solve it, if I add 4, it's equal to 7, and divide by 8, x is 7/8. Okay, now this one, I actually had to change both of the numbers into a common base. And the ones that we're going to see are based, most of the most common bases are 2 to some power, 3 to some power, 4 to some power. Those are the most common ones that we're going to see. Okay, I'm going to try another one here. How about this one? Here's a second one. 6 to the x minus 4 equals 1,296. Okay, Okay, well, I'm going to check this. Can 1,296 be written as 6 to some power? If I look at my yellow sheet here, I have a piece of paper, I go down to 6, and I go across the top, or across the row. Yeah, it's in the 4ths column. So I can rewrite that as 6 to the 4th. Okay, so I had to change the first or the second one, but this first one doesn't have to change. Worked out nice. If I look closely, they both have base 6s. They're equal to each other, so my exponents are the same. I can write a little equation for my exponents. If I solve for x by adding 4, x equals 8. So that one I only had to change one of them. Okay? Okay, I think we're doing okay here. I got one last one that I like to try here. And here it is. Okay, here's number 3, the third and final one. I have 81 to the 2x minus 3 equals 9 to the x plus 3. Okay, so I'm looking at my base numbers. I have an 81 and I have a 9. Okay, and well, can the bigger one be written as the smaller one to some power? Okay, so let's see this. Can 81 be written as 9 to some power? Oops. And I think it can. And most of you guys probably know this, but 9 to the second power is 81. Okay, and certainly you can use your sheet here. If you go down to 9, the first one over, first column is squared. 9 squared is 81. Okay, so I have base 9s. This one's going to stay raised to the x plus 3. But this guy, even though it's that, it's still going to be raised to the 2x minus 3 power. Okay, so I have to finish this by doing a little distributing. That turns into 4x minus 6 equals 9 to the x plus 3 power. And now you can clearly see that they both have base 9s. And if the bases are the same, the exponents are going to be the same, and we can write them equal to each other and solve it. So over here I'm going to do 4x minus 6 equals x plus 3. If I move my x's to the same side, I subtract x, I get 3x minus 6 equals 3. Add my 6, equals 9, divide by 3, and it looks like x equals 3. And one thing I haven't been doing here on these last couple problems is checking my answer. Is there a very easy way you could check your answer? Yeah. I could take this 3 and I could plug it back in here. I'm going to do that really, really quick. If I take a 3 and I plug it in right here, and I take a 3 and I plug it in right there, it should be the same number. Okay? If I plug in 3, 3 times 2 is 6, 6 minus 3 is 3. 81 to the third power. Okay? If I plug in a 3 right here, I get 9 to the sixth power. If you did those on your calculator, just a really, really quick check. 81 to the third power is 531441. 531441. And if I did 9 to the sixth power on my calculator, turns out to be the exact same thing. 531441. Okay, and those two things are definitely equal to each other. Okay. All right, so we did a lot of things there today. We converted from radical form to fraction form to radical form, or exponential form, I should say. We simplified, we evaluated fractional exponents, and hopefully we're good. Thanks for tuning in.